My name is Chris. I wanted to thank all of y'all very much for coming to attend our workshop today. And we really appreciate your support of our small business. This presentation is going to be presented by Tom Taylor and Lance Borden. And thank y'all very much for coming.
He was one of very few people on consoles saying we're ready to fly for the shuttle.
That's amazing.
That's true. Wow. That's actually true. I could either approve to launch or I could cancel a launch, and you never wanted to do that. You know, if our equipment wasn't working properly, then we had to hold the launch, and that only happened one time, thank goodness. And but other than that, everything always worked perfectly. The systems I had was the TACAN, which is a tactical air navigation. It was a radar system which told the shuttle where the runway was from 400 miles out. And then another system was a microwave landing system, which was another radar that lined the shuttle up with the runway and made sure it landed exactly right. And the other one was radar altimeters, which told them exactly how high they were off of the ground. So, and that all of those things always work perfectly.
Let me be brief, and then we'll kind of take direction. My career started very much the way it was with Lance, and maybe the way y'all are. I can remember being in junior high approximately, taking radios that were destined for the garbage can and taking them apart and trying to make them learn, try to make them work. And you learn very quick that some of them have high voltage in them. So it kind of took an interest. There wasn't anybody that I knew at that age that could help me. I finally found someone after a couple of years, and I made a career choice in high school, which happened to be Dover, Delaware. The folks were Air Force. And so I came to University of Houston in the late 60s and graduated, married, worked aerospace companies locally, and it was in support of payload development for the Mir, the shuttle, and the station. Very much the same path, but not the responsibility. I like to take the background, and but I still got gray hair as a result.
This is what we're going to build today, and here's a little power switch that we made out of parts, and so we'll play the radio for a minute just so you can see that this actually works.
So that's one tube doing that work, and the sound is amplified by that computer amplified speaker up there. So he picks any of several stations. Right now we bring our own station, and we get to hear it across the room with that amplified speaker.
Now, one thing I'd like to show you, speak over this thing, that we'll just turn it off for a second. Okay, this is the vacuum tube. It's what does all the work. Can you see it up there? Well, my hand in front of it, right here. Yep. The vacuum tube. And this is a variable capacitor, okay, right here. All right, that's a variable capacitor. It has a knob that you can tune it with. This is a coil, which is an inductor, all right? And so the capacitor and the coil work together to make a tuned circuit. So we can actually tune the radio to different stations. Right now we have our own station.
Let's just start into it. We're going to introduce some terms. I know some of y'all have seen that. I'm going to try to circle the term that I'm talking about here. And basically this term is resistance, the first one. And we see an equation for that from Ohm's law. Let's talk about resistance. Let's say we have a voltage, any kind, AC, DC. In this arbitrary example, we use 100 volts. we're going to put two resistors in series. One of them, we're going to call it 2X, the other one called X. That could have been 200 million on the top and 100 million on the bottom. It doesn't make any difference what X is. We can just say this X equal 10, 20, and 10, for example. The question I give you is, what is the voltage at this point, right at the junction of those two? Look close. This is 2 and this is 1. A total is 3. 3 into 100 gives 33. And so the voltage from here to here is twice 33. And the voltage from here to here is 33 volts. That's important that you just saw that you understand that. Okay, so we're talking about voltage drop. That's the term that I'm dealing with right here. So I had a question mark here. What is the voltage drop at this point? And it turns out that's the voltage V2. And so if you think about that, just stare at that, you're going to see this will be very common to look at things this way as you go on and what we do later. It's not critical, but it's just a building block. So let's talk about resistance a little bit better. Here's an analogy. A bucket of water, I tried to show it in the red here, and I punched two holes in the bottom. One of it's a smaller hole and the other one bigger hole over here, and we got a lot more water streaming out this hole over here as the bucket drains down. Obviously there is less resistance to water escaping out a larger hole. We got a bigger stream, the hole is larger, there's less resistance to prevent that water from coming out. And so here is the smaller hole, greater resistance, the water wants to stay in there a little bit longer. So that is an analogy indicating what the word resistance means. I hope that one is clear. So here we dealt with the voltage drop. Looking back here, 1/3 of the resistance is here. That says 1/3 of the original voltage, which is 100 volts, is here. 1/3 of 100 volts is 33 volts, therefore V2 equals 33 volts. Now, the term voltage drop means with one voltage with relation to the other one, V1 minus V2, that's the voltage drop. Here, the voltage drop would be V2 minus 0, because this is 0 volts down here at ground. And so V1 minus V2 is 66 volts, and some change, V2 minus 0 is 33 volts. Now what I've just said here, because it's a resistor, that means for any frequency, AC or DC. Now, we're going to talk about AC here in just a second to be sure you know what I mean by AC. So once again, resistance, same thing for AC or DC, any frequency. Now if you were to plot on a chart, and I forget which one's ordinate and which is abscissa, but X and Y, the change of current with respect to voltage, you will see that there'll be a straight line out there for a given resistor. That's called a linear relationship. This is a linear relationship. There's nothing squared here, there's no square roots, there's no exponents. It's just straightforward linear relationship for these terms. So we get a linear line type of response or relationship between the voltage and the current. And it turns out the slope of that line, some of you remember how to compute the slope, but the slope of that line tells you the value of the resistor. And slope is y over x. Y2 minus y1 over x2 minus x1. Now let's spend just a second on alternating current. If I get a ruler and put it on the end of the table and strike it, that ruler alternates until it settles out, vibrates until it settles out. That's alternating. Voltage, like from the power plug in the side of your wall, is alternating 60 times a second. It's 115 swapping back and forth 60 times a second. I exaggerated that 115 a minute, but I will leave it simple. DC, direct current, is your batteries, everything. All batteries. Car battery, flashlight battery, batteries in this, direct current. Current goes one time one way until you turn the switch off. Never reverses and goes the other way. Directly out. Okay? So that's the difference between alternating current and direct current. So for a resistor, This line is true regardless of the frequency, regardless of whether it's AC or DC. All right, now I'm going to move to something related to resistance, but we're going to flop the term around. We're going to put it upside down, the reciprocal. We're going to talk about that in a minute because it's important for tube learning. But before we get there, let's talk about bias. Bias, let's say that every time I'll turn on the television, I'm hearing something being said about the school board, or something being said about production of airbags. And every time I start to hear that word, I start getting mad. I start thinking, you know, they're spending our money, they can't get this right, they've been doing it for years, they sold 100 million of these things and we got them out on the road and it's a problem. As soon as I start doing that, I'm exhibiting, I have a bias against those manufacturers, the inability to learn and solve the problem. I've got a bias. In the political world, you must always, obviously, know what a bias would mean in that world, but it's a leaning. Okay, so in the electronic world, a bias is a voltage there, a force applied to do something in the background. It kind of sets the stage for proper operation. A bias voltage is kind of a small nudge that's always there. I'm providing a bias force on this table right now. Okay, so to make a tube function right, we're going to have to put a voltage called a bias voltage on the grid. Now, some of you might not have been in an earlier session. That the internal construction of a tube is like a bunch of concentric rings, like the Target that you might see for the Target department store. At its core is a heater. It's throwing off electrons. As soon as you put voltage on it, it's throwing off electrons, and it turns out it's a piece of metal. It's doped with certain elements, and when you get it hot, it's throwing them off. They're just going everywhere, but you want to focus them, get them accelerating under control to an endpoint. So surrounding this heater right at the core, once again concentric rings, is a control grid. A control grid is like a spring. A very fine wire, kind of stiff. You don't want it vibrating in there when somebody walks through the room. So it's a kind of a stiff spring, and it's got a little bit of voltage on it. It's got a bias voltage, a very small amount of voltage, and it turns out it's like the throttle in the car. You start controlling that voltage on the control grid, and you're controlling the flow of current that's getting further out into the tube. So another way of looking at this bias voltage is your light switch. A throttle is a means of controlling how fast the engine speeds up in your car. A light switch is a means for controlling an entire array of light fixtures across a room. You move a very small switch, and all of a sudden 20 amps of current goes out across LED lighting. So a very small move here tends to control a large task. Now there are two types of light switches. There's a type you can move slow and it dims the lights, and there's the traditional old school light switch. You flip it and it toggles over to the other side. That's digital, off, on. Analog dimmer light switch, off, on is digital. Okay, just to let you know. And tubes have an application in the digital world. As a matter of fact, the earliest computer used tubes, just like this one. 12A-T7, 12A-U7, 12A-Z7. Okay.
Well, actually, before that they used relays, like even before relays.
Exactly right.
And
I saved this sign for students that pay attention and have good input. You the man. Okay.
And then even before that, one guy made one out of telephone switches.
Yes, telephone came early. That was the development of technology. Well read, very good. So I'm talking about a little throttle control out here on this control grid that's going to control those electrons being thrown off the heater. The filament is a heater. You turn out the lights, you light up some of these tubes, and you can see the little amber heater in there lit up. Now on this 1-volt tube, I don't think you're going to see that. There's not a lot of heat coming off that tube. Now, all of these electrons are going towards something positive. Electron negative, they're going to find something positive. And in the outer perimeter of the tube, just inside the glass, is a metal plate. Think of it as a metal cylinder. that is mounted on axis surrounding the business within, which is the grid and the heater at its core. Now, it turns out the world's not perfect. You can't get absolutely all those electrons through and out the tube without a little loss. Everything seems to take a little tax along the way. A little something is removed, and there's a little loss inside the tube. It turns out it's a resistor, the internal resistance that's in the tube. Now, how much is it? You got to go to the data book for that tube. Now, all these tubes have got an internal resistance, a little loss. You go down here and pick up some wall warts, a wall converter, those little black plug-in converters that power or charge batteries. It's got loss on the inside. It looks on the, you look on the label on the side that says 9 volts, 300 milliamp. That's only true in certain circumstances. You start putting 310, 350, 400 milliamp on that thing, and it's going to start failing. It's going to start rolling over. That voltage that it says on the side of the thing will not be available. It will diminish. It'll roll off because it has internal resistance. Even a car battery, as stout as it is, I mean, it's enough to weld a screwdriver to the frame, has some internal resistance. Far less than, you know, batteries we can carry out here. So just keep in mind that there is some loss within the tube. Okay, now ideally, if you want to get most power transfer from a tube into the load, a load, what is a load? In this example, it's a resistor, but let's say it's a transformer, let's say it's an LED, let's say that it's another circuit downstream. It's whatever you want this tube to do for you. It's going to drive that load and do some work. You're going to want to have, according to a formula found in many books, it's going to say you want to make this internal resistance pretty much match the resistance of that load resistor. Equal to. Well, if they're equal to, then half the available voltage applied here will be at this point. Remember our voltage divider we had earlier? The 100 volts, 2x, 1x. We used an example of 2 to 1 ratio. Here is 1 to 1. Both of those are equal. So, obviously, if you're applying B plus, whatever it is, 100 volts, then B plus 100 volts divided by 2 will be here, because your design objective is to have that resistance, which is within the tube itself, equal the load resistor, the area where you're going to do some work. That's an important relationship to keep in mind when you're going to pick a tube, arbitrarily pick a tube and make it work. So, I'm sorry, I'm talking fast again. Let me pause. Any questions so far? Sorry. I enjoy this. So, we have on our example over here a tube which is a 1AE4. Turns out the data of the characteristics of that tube is very similar to a 1T4. You don't have to go out and wring your hands looking for a tube like this. Very, very soon now, Chris is going to have some tubes by that part number, but it turns out there are tubes with similar characteristics. Actually, tubes are very much similar. A rock is a rock, a tube is a tube, almost true. So that 1 means the filament is lit up with 1 volt. So when you look over there, that's imprecise. I should have said 1.4 or 1.5 or maybe 1.6 volts. And so that 1 means that it's a 1 volt filament, approximately 1 volt. And when you look over there, you're going to find it's a single D-cell battery that's powering that tube for the filament, for the heater, for the thing right at the center that's throwing off electrons. Okay, so another key characteristic of the tube is something defined by this formula, 3 terms, simple linear relationship, and before we used the term resistance. Remember the water escaping out the holes in the bucket? There's some resistance to the flow of that water escaping out. We're going to take that term, that equation, we're going to make the reciprocal of it. 1 over resistance is equal to conductance. We have 2 parameters on this one chart that's key to tube design. You want the internal resistance to approximate the load resistance, whatever we're going to do with that, and you want some knowledge or awareness of the mutual conductance. Turns out the best, most costly tube tester you can buy is going to be measuring mutual conductance. Obviously, they think it's important because you can still today spend $200 to $600 on an antique tube tester that does that good. And you can spend that much money paying someone to calibrate it. Okay, so how do we get these numbers? How do we get the mutual conductance or the bias? I mean, where do we get these numbers to determine what we designed to? It's in the tube manual. It's in this particular reprinted thing, but you can find originals in this good shape, and you can go into the data, see that performance curve? That tells you what that specific tube is doing. But in the tables here, you can read down through here and you can say, what is the internal plate resistance? And what is the grid voltage? I can't seem to talk and find this at the same time. And another important parameter we'll talk about in a minute is what is the maximum current that tube can take care of. Turns out that little wimpy little tube right over there is only 3.5 milliamp, flat out. That's all the current it's going to handle. You can't light an LED real good with 3.5 milliamp. So, but you can hear a radio station. We got that going over there in just a minute again. So 3.5 milliamp, that's the best that little tube can do. But there are tubes that you can still get that were produced in the 70s, for example, that will do better than 1/4 of an amp at, and this is actually kind of big because they ran color television sets, everybody's living room, at 800 or 900 volts. Now why is that important? You get 4 of those and you can go and have a 1,000 watt RF amplifier on your ham radio. Several manufacturers made it using those tubes that were called sweep tubes. And so they were stout. Now they'll change your fingerprint in 1 minute. From the time you turn it on, it will change your fingerprint. But there are tubes that would far hotter than that, values I can't even possibly estimate. So, so the parameter you're looking for, the bias voltage to make that tube do a particular thing, and how much is its maximum current, and what is its internal load resistance, all in the data book on the tube. Now, you don't have a data book? Go home, look on the web for Sylvania data, Sylvania tube data. You'll get a website that will make that look insignificant. It's curves, it's data on everything Sylvania, one of the major manufacturers, made. Okay, so what do we do with VG, bias voltage? That's the determining factor. Remember I called it a throttle, that voltage that you're dealing with here on the control grid? So it turns out you change that voltage and you can change that tube from an amplifier, like you would have at your guitar, to a detector, like we have going on right over here. It turns out the conditions on that tube over there is doing both. It's detecting the signal, it's irradiated in the air, and it's amplifying it. That all had to do with what the bias voltage is doing for us there. That is a grid leak detector, and the implications of that term, if you go to Wikipedia and look it up, is that it's doing 2 things. It's the characteristic of the tube that's amplifying, and due to its nonlinear relationship on the inside, it is detecting. Remember we had a curve earlier that was linear, linear? That is what is characteristic of a resistor. But if you take a diode, or you take a tube that's performing as a detector, you're going to find that it's squee-hawed around. It's non-linear, maybe like that curve you glanced at there. So we have another parameter that we're interested in on the tube, and that's the maximum plate current. Remember, 3.5 milliamp on that tube over there. Now, what's important about that? Oh gosh, I'm getting...
That's okay.
That's me. He's pointing out I'm long-winded. Okay, so the important thing is, let's say you have a radio which you could have bought that was portable and days gone by and it had 5 tubes in it. The maximum any of the tubes could have done is 3.5 milliamp, 5 times 3.5 milliamp, about 17 milliamp. That's nothing on a battery. So the early portable radios had tubes and they were battery powered, no power cord. You took them to the beach. Okay. Yeah, can I overrun?
I have a question.
There's a question back here.
Yes, sir.
So, turn your thing back over. So, Are you trying to generate a particular voltage out with that circuit? Is that the purpose?
You want to set the conditions up for the tube to be in the center of getting ready to do its job. You want the ideal, they call it quiescent, normally doing nothing, position of the tube is to be in the center. Now, send it a signal, it can go up or down. Okay, so you're setting the preconditions for the tube to do something for you. That's where we're headed with this.
So you change the bias to change the voltage out. Is that what you're doing?
See, how would I best describe it? Let me try this, see if it works. We have a dimmer on all these lights in here, for example. And we go over to the dimmer and we turn the dimmer down, dim all these lights. Everybody can still do everything they want, but there comes limitations in what you can see, for example. You no longer have enough light to see well. That's like shifting the bias on a tube, because if you can't fully get the voltage swing out of the tube, at one point it's going to hit the rail. It's going to go completely off. And when the waveform comes back positive, it's back in an operational zone. Conversely, if we have too much illumination or too much bias on a tube, then we're somewhat blinded under some conditions, and adding more light is not going to make it any better. So if the waveform went more positive, it's going to, we're not going to be able to see the product of that sort of thing. It's kind of a weak analogy.
So is it throttling current? It's throttling current, right?
Yes, sir. The grid bias is doing that. For a voltage in, that's your throttle. You are actually, spot on right, controlling the current flow within the tube. That's a good input right there. So some of this will become more clear as we go on. I would love to spend as much time as y'all want, so we'll just go as we go. Amplitude modulation, AM. Your AM radio in your car or your house or whatever. Some people call it antique modulation, AM. Okay. So it was the first modulation that really came about, or we're saying is there, and simply we're going to put something on top of something. And the best analogy that I can come up with is when you press a note on a touch tone phone, it's actually mixing a tone that has to do with the row and the column that button is mounted in. For example, the number 4 is in the first column, second row. You press the number 4, you get a curious sound that does not sound pure. It's because one note is modulating the other. It is two tones that's come together. That's the modulation that I'm talking about. So what are we modulating in AM? We're going to modulate a carrier, which is at 740,000 cycles if it's KTRH, KTRH meaning the Rice Hotel, which is still, the structure's still down there, but that's what that was for. So, and nobody's going to hear this with the ears. We can't go over about 4,000 hertz, and maybe if we're young, 8,000 hertz, and women and men are a little bit different. But you're not going to hear 740,000 hertz. That's RF, radio frequency, RF. But it's what the carrier is used to get the intelligence out. Intelligence is both speech and music. And so it's the medium, the transport medium, if you will, to get the intelligence out there. So we're going to modulate that. What we do is we mix the audio, my speech, with this carrier, and we get a composite waveform that looks like this down here. This is not very good, but if you look at the red, this is the audio portion of the signal that's out on the air. Now, the best way to see this is if you have an S meter on a radio, whether it's in LEDs or it's an S meter that moves, and you come up on a station and the guy goes quiet, like between commercials, your S meter stays right up there, didn't move. The carrier is still there, but you no longer hear his speech, so it's not modulated at that point. So the carrier was there, but the waveform come out as a pure sinusoid because the S meter stayed right where it was, didn't move. And his speech, the envelope, the composite signal was changed because he was not talking. Now, how do you get this recovered in a radio like this. I don't know how to speed this up. I'm sorry. But we're going to need to rectify or detect it, and we're going to do that with a diode, or we're going to do that with a detector, or we're going to do that with a rectifier. All in terms are almost synonymous. That one is working like a detector. A diode is like germanium or silicon diode. We use germanium because it has the lowest forward loss across the part, 0.25 volts. Silicon has like 0.65, 0.7 volt loss across the device. And so both of those are going to cut half of the sinusoidal waveform away, leaving the other half.
And when transistors were invented in 1947, the first one, well, the germanium transistor was invented in 1947, but then the silicon transistor was developed by Texas Instruments in 1958.
That's outstanding. Let me sit down a while. That's very good. That's very good. What's your name?
Maxwell.
Maxwell. You're invited back. Okay, so yeah, it is. So how do we get this type of rectification in a tube that might be thought of as an amplifier? We're going to change the bias. We're going to shift that V sub G bias voltage around and set up the operating conditions for it to work. So we use a bias offset on grid 1. Grid 1 is the control grid, the throttle, and we're going to take advantage of the trait inside the tube, which is nonlinear. Remember? It's not like a resistor, it's a nonlinear curve in the tube. So the question is, what is V sub G, that bias voltage or grid voltage? And we're going to have to probably do a little experimentation to polish it, but there's certainly ballpark numbers in the computation I'll show you in a minute. So once we rectify it or detect it, we have half the waveform missing. We have then this other half that's there. And so we're going to clean this up a little bit by putting a capacitor. Now, where did I get that? Look at the trait of a capacitor. It is dependent upon frequency. 2 pi 3.14159 pi, is in this formula, and it is frequency dependent. Resistor was not frequency dependent. Both the inductor and the capacitor are frequency dependent. The formula for both is going to have that F term in there for frequency. So look at it. We have a constant 2 times 3.14159 plus 2 variables. Well, that's it. That's a straightforward linear relationship, and one of them is frequency, the other one is the value of the capacitor. So why is that important? As the frequency goes up, the capacitive reactance goes down. It's inversely proportional. As the frequency goes up, that becomes a short. It's headed towards being a short. So as the frequency is higher, this red in here is the higher frequency, that capacitor is going to snuff it out, the higher frequency, not the audio portion. So the way to get from this detected signal to pure audio that we can listen to is to kill off the RF, the high frequency component. Let me skip past that one. Good basic fundamental. Turns out an inductor is very similar, but it doesn't have a reciprocal relationship. So I'm going to just gloss past this one. This in blue is the computation for what you do with 2 capacitors of identical value in series. We actually do that in the radio circuit here. Why? We didn't have 22 picofarad capacitors, but we had a whole bunch of 47s. What's half of 47? 23 and a half. So what we did is we put 2 capacitors in series and come up with the value we needed in the kits you're about to build. So let me run past that, and I'd be happy to spend more time later, but into the world of inductor. Okay, thank you. In the world of inductor, you see a relationship that's not 1 over that. It is 2 pi again, times the frequency, times the inductor value, but it's not 1 over 2 pi FL. It is still frequency dependent, and there's our little parameter, our little inductor value right there, which says in a way that the relationship between voltage, if you put an inductor in series with a resistor, the relationship between voltage across the inductor versus frequency is linear. Did we spend time on the capacitor? It's linear, but it goes the other way. You see that? One's in the yin, the other one's in the yang. One of them's going down with frequency, the other one's going up. Now let's say you superimpose one over the other, like that LC arrangement that's right over there in that radio. You come to a point where these lines cross over, a sweet spot. We're going to call that resonance. When L and C having similar reactance to one another, we're at resonance. Now, because this is kind of dramatic, I want to show you this that's set up here. I have a signal generator. It is set on band B, which is the red scale, which is AM radio band. We have a scope. We don't care anything about how this waveform looks other than it's going to collapse in a minute. I'm going to turn a knob and it's going to collapse. And we're going to be showing that that is going to be the resonance between the L, this inductor here with the ferrite, and this capacitor here. So we can change either knob. We can change the frequency this LC arrangement is looking at, or we can change the L and C combination, the resonant point, and it'll do the same thing. So let's see if we can find it. We don't need power. I think I still have it set up. Okay, do you see that right there? Sweeping past that, that waveform went from almost a full scale, right there. And come on around with our frequency, and we find us a sweet spot, resonance. That's what's taking place when you tune a radio. That L and C reactants are crossing over, and we're getting the energy voltage from the capacitor, the energy current from the inductor to start shaking hands. Okay, kind of complementing one another. So there is a formula for that, and I'm sorry, but it is the formula. It's got a square root in it. I'm not going to spend any time on it, but you can predict this behavior. It's called resonance, and there is 2 pi again with the square root of L times C. Simple product. As L or C goes up, frequency does what? Tell me what frequency?
Goes down, at least
Exactly. Okay, straightforward. L and C parallel combination. That's the blue reminder to do the demo over there. Now, this is a frequency scale to give you a perspective of what this radio in the kit will do for us. If you look at frequency spectrum, we have in the world of AM radio what's called low frequency, and these breakpoints are multiple of 3. If you look at that, this is megacycle or kilocycle or cycles, but it's 0.3, 3, 30, 300, 3000. Okay, those are the boundaries of each of these. Low frequency is 0.3 to 3 kilocycle. High frequency, which is ham radio, is 3 to 30 megacycle. VHF, your television, your lowest television frequencies in airport communication, aircraft communication, police communication, and a bunch of other things, is from 30 to 300. And ultra high frequency, which includes some cell phone and so many other things, I think even, I know this is true, ham radio and aviation, is 300 to 3000. Turns out, it's no coincidence that these are multiples of 3. There is a formula that has to do with wavelength and frequency, and it equals a constant. And so we can convert these frequencies to wavelengths and multiply one times the other, and it always comes out with the same constant. I'll let you look that up if you're interested. This is our schematic of this radio we're going to build. Now this looks like a tough one, doesn't it? Let's see, 2 fixed capacitors, 2 resistors, 1 inductor, 1 variable capacitor, 1 switch, and 2 batteries. Please. But it's going to get us AM radio. And it's an example of what was built years ago that people used to buy the parts for, because there were no radios to buy back in the early day. You had to buy the parts and build your own. I've got some of those homebrew radios at home, and they work wonderfully. Now, fundamentally, there were 3 batteries involved in the very, very early stage. They found a way to get rid of one of those batteries. The plate voltage was provided by the B battery, B, biggest battery. Maybe that's the way to remember. B battery, biggest battery. The filament voltage was the A battery. I like to think of as we don't get to first base unless we come up with a hot filament. So you begin somewhere, you begin with A. A battery is the filament battery. So that left one C, which is the grid. All right. So I know people are looking at me and the time is coming up. So this is our assembly instructions. Lance is going to lead you to do that in the kit, if you should be part of the kit building. I wanted to highlight a little something before I step away. We're going to show you how easy this is to do. We went over through some of this theory, but right here at EPO, you can buy kits that not only will look better than a good effort we've got going on here, but you're going to come with instructions and pictorials and 2 forms of looking at the circuit. Great deal of detail, some history like Lance was sharing with you a minute ago. Everything you need. The board has got holes in it to run your screws into, and the highlights of the kits can include no AC power required for any of them. You don't have any threat of getting shot.
Can you go back to the schematic? Because I want to take a picture so I can...
Oh, okay. Yes, sir. Glad to. There are other highlights I'll go over in just a minute, and I think they're strong. That's the reason why I mentioned them. Okay. So, no AC power, no safety issue there. Some with minimal or no soldering. Full instructions, history, pictorials, and everything provided. Some don't even use batteries to hear stations. How does that happen? Well, actually, Lance has received email from people asking him, how do I turn my radio off? There's no batteries on it. There's no power at all. He has 3 forms of such a radio over here. Right. 3 variations. Okay. And by the way, when they get to be this simple, the price is down. These are also on soft pre-drilled boards. The boards you're going to work with today are a little firm. They're plywood. How does plywood come together? It's sawdust and resin.
Place your board with this away from you, and this is towards you, okay? All right, so the first thing we're going to do is we're going to mount Fonstock clips to the board, and that's these little spring clips here. And so you should have, let's see, 1, 2, 3, 4, 5, 6, 7, 9 Fonstock clips, okay? They're Fonstock clips, so we just call them Fonstock clips, okay? Then, we'll get one. Okay, and then you're going to find screws in the kit. Now you got let's see, at least 2 different kinds of screws. One is a number 6 screw. Let me see one of those. Those are the number 6 screws. Yeah, these are 1/2 inch number 6 self-tapping screws. Okay, so you're going to have. I think you got about 12 of these screws. Okay. Or maybe 10 of them. Yeah, you should have 10 of them. All right. Okay. So get your number 6 screws out and your Fonstock clips out. Okay. And the first thing that you're going to do is you're going to put the you also have solder lugs. Okay. And let me see a solder lug here. There's no solder lugs there. Yeah, you should have solder. Yeah, there's your solder lugs.
Can you hold one up?
Yeah. Okay. Get the bag open.
Oh, a little bit.
Okay. And I'll give this back to you. Okay, these are the solder lugs. They're just a little flat piece of metal with a bend in it. It has 2 holes or 3 holes in it. Okay, everybody got your solder lugs out? Yeah, okay. Right, so, there's a, there you go.
Yeah, okay.
Okay, start at the left side. This is the finished radio. Start at the left side, and I'm gonna pass this around. Don't touch anything on it, just pass it around. And see how the solder lug is mounted under the font stock clip and then screwed to the board, okay? This thing we're going to do next is not too tricky, but you're going to pay attention, okay? Right. So what we're going to do is I'm going to pass this around first. We're going to make one of these, okay? See how that's double-sided tape is trying to cut. It's got one piece of sticky.
You're trying to call out the emerald.
So I'm gonna make the first one. Okay. So we're gonna have to. Okay, this tape is 1 inch wide, and we need it to be a 1/2 inch wide. I'm gonna cut all this off right now because it's kind of in our way. This tape has a pattern inked on it. Everybody see it has a pattern of little X's and stuff? So that gives you a guide of where to cut it. So we're going to cut a piece out about this length, and we're going to cut it halfway, half down the middle, so we can make 2 pieces from one of these. Okay, so I'm going to split the tape. This is a little bit hard to do.
He doesn't jump out. He doesn't jump out, just like you're talking about.
Okay, so now I have 2 pieces, 2 pieces a 1/2 inch wide. Okay, see that? Okay, I got 2 pieces a 1/2 inch wide. So I'm gonna hold this on here, and I'm gonna cut out a piece that's the same length as the one that's on there. Okay, and I'm using the little X's down the middle as a guide. So I don't know exactly how long this is, so I'm just going to use this template to cut it. Alright, now I have a piece that's exactly that length. I think I'll make another one that's exactly that length, so there'll be another one for somebody else. Okay, I'm going to stick it right there. Alright, so I'm going to take it now, and I'm using this as a pattern. I'm going to cut the small piece off. Okay, here's what I got. It's the same thing as that. Okay, everybody see it, right? Okay, I'm going to put it on the pattern here. I think we're all going to have to pass the pattern around. And I'm going to cut an end piece that's exactly the same length as the end piece that's there. Little end piece. Got it on there. Then I'm going to cut the piece that's in the middle. This one I accidentally cut it in a little bit of an angle. That one, try to keep it straight. Okay, so then I'm going to cut the middle piece out. I'll pass this around so everybody can see it. There's this middle piece. And then the end piece should just be the right length, okay? Okay, so that's what I've made. I've cut 3 pieces out, okay? See that? Then we're going to take the middle piece and we're going to stick it right next to it. There should be 4 little holes on your board that shows you where this piece goes, okay? But this is where the coil is going to go, okay? You see your 4 little holes right here? Okay. So you just put this piece right where the 4 little holes are. Okay. You stick it down. Okay. Then you take your end piece and just mount it right next to it. It looks like these nails are a little close together. So I'm going to have to trim this one down. These screws, the number 4 screws are a little close. So I'm going to just cut a little tiny piece off the edge of this tape.
I'm usually on the board. Whenever we change something.
Put that over here. I'll stick it.
See, if these are edited,
Okay. Make it fit.
give them a mix.
Alright, and it just goes on the end of what we just made. And we stick that down, okay? See how that looks? Okay, everybody see how that is? Okay, alright? Okay, and then next one, you see it? Okay, how that is? Okay, so we take the one in the middle and peel that skin off of it. Okay, like that. Right? See how that is? Okay. See? Okay. See how that is? Okay. Then this is the highly skilled thing that we have to do. We're going to cut 2 little pieces of tape and we're going to put them on top of that. Like, we're going to stick it right on the edge. So I've got it stuck to crooked. Okay, we've got one piece there. One piece here. All right. Now, you see how I have 2 little narrow pieces stuck right there? Okay. Okay. You see how that is?
Yep.
2 little narrow pieces on there. This is going to hold the coil. See how that is? Yeah. Okay. These 2 little pieces are right here. Okay. Stick this down real good. Just push on it real good. So let that stick to the board real good. Then on the 2 little pieces, peel the skin off of them.
You don't have to take the chime. I need to get my paper carrier over there so I can not hovers out.
Okay. So it should look like this.
Is this my bag?
Okay. Anybody want to pass it around and look at it?
You don't have it.
Well, you can use this as a guide. We'll be passing it around.
Thank you.
And then it looks like that, okay? All right. Now the next thing we're going to do is pretty easy. We're going to put another piece of sticky tape on here. And it's going to be it can be 1 inch. So if you use a little squares on here, the little crosses or whatever, you can use that as a guide. And you need to make this one the same width as the other 4 little holes that are on here. Okay, so it's going to be cut right here.
I think they're sharing. They're sharing on
Cut it right here. So I made a little rectangular piece, almost square piece. It's about that size. Okay?
Okay.
See Maxwell?
You don't have to.
I'll give it to you.
It's gone.
Okay, and then there's 4 more little holes right here. You see those? Okay. There's 4 little holes right there.
Yeah, is this for mounting the switch? Is this for mounting?
No, this is for mounting the variable.
Yeah, that's why.
Okay, so now we're going to put that piece of tape right lined up with those 4 little holes.
Like on the floor?
These 4 little holes. Okay, all right. And that's not what we're going to mount the variable capacitor to. Now, once we peel this skin off of the tape, don't touch these areas because it still needs to be real sticky. We're going to put some things on it, okay? All right. See how that is? Okay. So the next thing we're going to do Why don't you all just, okay, here's the tape. And I'm going to let everybody do it themselves. We'll just have to do it one at a time. Sure you go. We'll have scissors. And you want to copy what I did, and you want to put a piece of tape right here. Okay, so right here. Just like this one. This is theirs, but yeah, we can. Is it okay if we pass it around? Oh, sure. Okay. So if you want to look at this finished one.
Don't you have a pre-measured length sample or cut?
It's right here.
Say this.
I do.
Anybody wanting to trade their tube socket for the Advantage, we'll do that in the interest of time.
Yeah,
It's your call.
these are pre-wired tube sockets. Tom already put the screws on them. I mean the wiring. These tube sockets are already have the wire soldered to them.
Oh, okay, yeah, sure, I'll take that.
Everybody want a wire?
Goes in one way only, not rush. Anybody else?
Yeah, I think everybody wants one.
Yeah, we'll trade it.
Tube socket.
Okay, give him your old tube socket.
He did.
Okay, so you can give him your old tube socket. You have it? Oh yeah, you got a tube socket. I'm gonna take your tube socket. I'm gonna give you a pre-wired one. Okay? Okay. All right. Did you already trade it? Okay.
I didn't take it.
Oh, did you get a socket?
Thank you.
There you go, sir. Thank you.
Thank you. Thanks.
So everybody gets one.
Powerful Advantage here.
Thank you. Over here. You two.
You can give me both, I'll pass it.
You've already got
I got one already.
First we need to tweak it.
Oh, you got one? Yeah, we got a tube socket.
Very good. Everybody done?
Okay, they need a tube socket.
It goes in one way, so don't
Can't
rush.
get in the room and start waiting.
Thank you, sir.
Okay.
You guys figured it out? Yeah. Excellent. Something did.
Okay, that looks beautiful.
Wonderful.
Yeah, that's beautiful.
If you have strippers and you're waiting on something to do, you can strip the ends of that tube socket you just got. For those of you who have already stripped your tube socket and you want to move to the next step while you're waiting on the foam or the tape to come by, take your tube socket
Can you hand me the tape?
and take a close look at how it is on this example. You see there is a gap up underneath the tube socket. Only one gap. And it's facing towards the center of the board. Turn your tube socket over. Look for the gap in the pins. There's a pin missing. You see that gap? Pin missing? That gap faces towards the center of the board. That's what I'm pointing right towards the gap. It's facing towards the center of the board. So when you go to mount your tube socket with the two white insulating standoffs, you're going to mount it in this orientation. Now, notice that the pins stick out a little far, probably a little greater than the distance you have with the standoff, so you might have to bend the pins out, radially out, in order for it that doesn't jam into the board.
Radially like a starfish.
Yes.
Wait, so like,
So I'm pointing towards the gap, the one missing pin in the socket. It faces the center of the board. So if you're in a position, you want to move on ahead, you can take the two screws, the two white insulators, and get ready to mount it in the two holes provided on the board with your gap facing the center of the board.
The center, so it looks that way. Yes. Okay.
Okay.
Looks left.
Okay, so this is right.
The gap faces left.
Everybody see it? Okay.
Where'd you,
Okay, I want to show you something. When you put the knob on the shaft, put it so that it points perpendicular to the bleeds. Okay?
You want to center the play in the knob?
Yeah, you just turn it all the way counterclockwise until it stops and tighten the screw so it looks like that. Okay? So it just points to 9 o'clock. Okay? Okay. Now we're going to mount the coil. All right? your coil, and don't drop it. I'm going to tell you, the coils have very, very fine wire. It's extremely easy to damage it, so you got to be really careful with the coil. Okay. Open up your coil.
No, but it's ferrous, which means a magnet.
Yeah. What if you like it's
Ferrite, right.
Where does it? Cool. 4 years.
So the coils are hard to open.
What kind of age of wire is that?
Kind of statement now.
30 or 32, 34.
Became a bagger.
Do you
No.
mount it with the leads up?
Yeah. There's that with the ferrite. He was interested in, it was a 400 watt tweeter, and it had people live on top of each other.
So if you look
Can
at
you use the
this
same
right
one
here,
for a 500 watt?
It's just how much power you can put from play that higher volume.
We have
see how that works?
at the ends of the coil supposed to be.
Hold on. These wires
Don't rest it, just make sure.
I was alright. I mean, I grew up like that. It's the same weed child.
It is.
they are. Now, I want you to mount them.
Oh yeah, you're probably not used to that.
Okay, do what you do. Okay, go ahead and put them down, make sure that the leads are available to solder on the wires. Okay?
I try to put some of that stuff out here. It's a sort of.
Yeah, well,
Your wires that
Yeah, I'll pick it up first.
Yeah, it is.
I think with like adding a second tube, then I can like do so much more.
Close more big.
I don't know.
Fair enough. I think at best you would probably amplify the signal even more. I'm guessing, but that's going to be the pre-signal that you amplify, right?
Yeah.
So it's going to be really loud over there, but it's going to eventually go out so high, right, it's going to start cutting off the high range of the signal, and it's going to sound kind of distorted.
Okay, everybody got your coil mounted? Okay.
That's my theory. I don't know.
Okay, all right. All right, we're ready to wire the set.
Dad, when I take them out,
Yeah,
That's good.
That's good.
How many we're about to get to soldering?
Pretty soon, there's not much
Okay,
left.
now remember, you gotta really remember that these coils, fine wire, is real easy to break, okay?
But y'all need to be quiet so I can listen to you.
Now, you can do what I do if you want to, but, I'll get to that. Okay, Tom, it's time to wire them. You want to take over for a minute?
Yeah, Kim.
Here's the example. We're just going to have to show them how to hook it up, okay?
And it's not in your kit. We reserved the right to bring on last. You see this part right here on the board?
yes,
Capacitor,
I
okay.
did see that.
I'm going to give you one that looks a little different, but it goes in the same location.
Oh.
In actual fact, if you remember the presentation this morning, we talked about two capacitors in parallel. That is a 22. I'm going to give you something where two capacitors are in parallel, so it's half a 47 capacitor, 47 picofarad that's in here. So you're going to use that instead, and it's going to do the job, essentially give you a value of 23 and a half.
Wait, so it goes,
So you mean 2 times 223.5?
Just the opposite.
wait, so it goes,
47 divided by 2.
it goes
Well, that's the same thing.
Yes.
It's replaced, because
You're exactly right.
it's the exact same one, or
Right.
at least close
And now, one thing that Lance said is we're going to first tin our copper-coated nails. Tin meaning when the soldering iron is hot, we're going to bring solder and tip close to the nail and get a little solder around the nail so that when we go to lay the part next to that, we've already got one side prepared. So that's called tinning, when you get a little solder on the leads, and that prepares it so that it will adhere, will attach really quickly. And so go through all 4 of your screws and with solder and iron and put a little solder around the top near the head and get it tinned. And as soon as you do, you can then take this capacitor I just passed out and connect it to this location. If you look at this, it's an interesting thing. I have numbered these Fonstock clips in counterclockwise direction. And the reason why I did that is when you're looking down upon a tube socket, as it now is, the pins are numbered counterclockwise. And you think, wow, why did it go that trouble? It's because if you're a serviceman or you're wiring the tube socket, when you got it upside down, you got all the advantage. Everything is clockwise looking at you from the bottom side. So on the top, we're looking down on the tube socket, and it's numbered counterclockwise. There's 7 pins. So if you look at the tube socket, 2 of the pins are not even wired. And if you, can anybody tell me which pins are not wired looking down upon the tube socket? Which pins? 2 pins are not wired, consecutively numbered. Anybody?
3 and 4.
4 or 5.
What, who said the last?
4 or 5.
That's what it is. It's 4 and 5.
5.
Your socket, if I wired it right, should have the first 3 pins in a counterclockwise direction with wires on it. 4 and 5 is the ones that are void, that don't have components on it. So that's kind of important. That's the reason why I'm bringing it up, because if we're about to build in a mistake, I hope you can be part of the solution by saying that, and that's pin 3, not 4. Something like that. All right, so go ahead and get that one part on once you get all 4 of your... We need solder. We need solder. Yes, they do, and we only want rosin core. 6337.
Where do we,
6337. The 2 numbers should add up to 100.
where do we, can we start soldering?
Right up in here and get it nice and hot. It doesn't have to be dressed out pretty. Just get it in place electrically, it's going to be fine. And you're going to find out they'll bend a little bit, and if it didn't survive the bend, you didn't have it soldered good enough either. So it's better that you kind of have it a little out of position, and then when you straighten it out, if it fails, it's going to fail, it'll be right down, and you'll say, I got to dress it out. And when you're applying the solder, you're really applying it to the shank, the shaft of the nail just below the head. Yeah, you can do it on top of the head, but it gives you a smaller site to connect the wires. Everybody catch that?
So put it on the copper screw.
Okay, yes. If you're getting to this point, you are doing a good job, because you are about halfway finished with your working rate.
So we're doing this one, not this one?
And what's going to happen next is going to go very fast.
Alright, so all of it is soldered melting on the line, not actually sticking to the...
I see how quick it comes to it. Yeah, go ahead and clean it. This preheats.
We have 6644.
Well, it might work. You see that little ball of solder on the top? Solder, just take your tip. It flows.
You want to get it all the way around the nail?
Yes, ma'am. And it just loves to flow once the conditions are right. Just keep your tip on the copper. Keep your tip on the copper, and then feed that solder in. And when the conditions are right, it just pulses around. So you're transferring heat, and this is the medium that allows the heat to be transferred. In case you've always wondered, solder is made of tin and lead, and that's melting at 640 degrees. It'll burn you. Don't ever use lead free. Should we not use this? Let me try it if I can on yours, and no. It may be just fine.
Did you get burned?
It's a matter of what is the melting point. That's it. The metals are the same. It's a matter of melting.
By the way, I was thinking about doing it.
Wants to show you a battery. I think we can order that battery.
That point that it melts is called the
The guys need some 64.
and actually it melts at a lower temperature when the right percentages tend to lead than if your percentages are way off. It melts at a higher temperature. Kind of bizarre.
I think that would make like...
So it's like magic.
So,
Solder, anybody?
so
Yeah,
not
it's on the
the
Okay, so we'll find the prototype. Now, what I did do Okay. Is I prepared a wiring sequence. And I hope this is understandable. I'm at some risk here by showing you this, but I thought it was right when I put it together. So here is the sequence you're about to do. TS is tube socket, pin number 1 to nail 3 to capacitor centered. Here, for example, tube socket pin 3 to FON stock 4. Remember I said tube socket pins and FON stock clips are run in a counterclockwise direction. Okay, so so if you're in doubt, let's pass this around and take a look at it again. You can start and go in any order, but intuitively, the wires coming off the pin are kind of going to go in the direction that it is. You're going to find 3 of the wires. 3 of the wires are exactly the same length. The longest wire is on pin 1. Is on pin 1. No, the shortest wire is on pin 1. The longest wire is on pin 7.
Hey, we got that Tom right here.
You put this on the check. You gotta watch out.
If she can do it, that's great.
Hey, can you hold that up for about a...
Yes, sir.
Just say, oh, sorry. Zoom in now.
Just the nails.
Are the nails?
I don't
Good shoulder workout. Sorry.
FS is fat as off plate.
Yeah, I was gonna get your...
That's those little... Oh my gosh. Oh, I'm impressed. Good job, bud.
Oh, yeah.
Oh, yeah.
Is that 3?
Which one?
Shortest is number 1, right?
Can I see the
Shortest is 1, longest is 7. And you got your gap pointing toward the center, so it's going to be right.
Tom,
can I see
to cap center.
So this.
Is it supposed to go in there
All
somewhere?
right, so 1, 2, 3.
Hey, can I see the board?
Perfect. All right.
Where's the finished board?
Justin, your turn.
We'll get that. Get a tube.
Let me see. Do it again.
Where do you have switches?
Switches are straight down this aisle underneath the birds.
Okay.
There you go.
Oh,
See? So you've got the critical voltages there where they belong, and I see a coil is connected, and the components are right. You're probably
Takes some effort to get those tubes out.
Yeah, I don't want to...
Pardon?
Don't forget to put your antenna on it.
Just push it in?
Yeah, in there too.
It'll only fit one way.
Anybody else?
Oh, good.
There we go.
I was looking for something there.
This one. Okay.
No, they're not.
Those are my auto ranging at all.
Those are yours. Okay.
Doing the box of wires.
Okay. I get that thing.
About through you.
because I thought maybe we had to be over there.
Maybe, I don't know what the,
Oh, I turned it off.
It's okay. No, it's okay. I also looked at the
supposed to
wrong
work on
one.
A and